So specific functions. So it's every one is about functions, but this one is about functions that are specific, more specific than what we have seen. So the specific functions that we have seen were pretty much go up to quadratic, and we studied fairly thoroughly. This time there will be more. Okay, so there are many specific functions that work in a specific way, and they have to be studied. And all what we have done up until now is a background as what is the question that we want to ask about those functions. So, such as domain range, for example, one-to-one onto, what's the inverse, because the inverse will produce more and more functions. So every time we introduce a new class of functions, we take its inverse, and then we have yet another class of functions. So that's the build-up what was for. So we'll start with the first class of functions is polynomials. So we already had two classes of these polynomials in the recent past. Those are linear polynomials and quadratic polynomials. Okay, so mx plus b, okay, a function, and say f of x is equal to ax squared plus bx plus c. Okay, typically we impose extra conditions that the if a is equal to 0 for quadratic polynomial, it does not have the quadratic term, so which will make it a linear polynomial. And so if we want to classify them in that manner with no overlap, then we would impose that extra restriction. Okay, so so we're looking for more of these, and the whole hierarchy of polynomials appear. But if you want to have one definition that would include both of these, in contrast to other functions that we have seen, is that we do only we don't do a division. There is no division here. So polynomials are functions computed from x by addition, division, addition, subtraction, and multiplication. So there are no other so first of all, there's no division, so there's no chance of dividing by 0. So there won't be any trouble in that respect. There are also no other functions are involved, no square root, no trigonometry, whatever exponential function will not come up. So anything else does not come up. We use only these three algebraic operations. And at no point you can divide by 0. There is no division. There is no square root or anything like that. So right away we conclude that the domain is negative infinity. Okay, so that will make our life easier. But it's still a very large class because, as you can see, there are no restrictions on how many operations of this kind we can carry out. Okay, so you could go starts with x, then add 2, multiply by 3, multiply by x. That's also possible. If you keep multiplying by x, that's what creates real complexity here. Add 7 and so on, and you can go on and on, and that will be at the end you will have a function which is called a polynomial. Okay, you can certainly see how you can do it, how those two functions in the beginning of the list, 1 and 2, how they can be acquired in that manner. So you start with x, then multiply by itself, then multiply by b, add together, add c, and there is nothing else there. Okay, so if I take this function, then if I want to now algebraically instead of kind of a flowchart style, I'll have x plus 2 multiplied by 3 multiplied by x, add 7, and then I could keep on going with as many parentheses as necessary, and that every time it will be polynomial. Okay. So that said, I could add more if necessary, say multiplied by x again, and plus 17, and so on, and you can keep going, you can imagine. So, certainly there is an end to it. We cannot go on forever, but we carry out these primarily two operations, addition and multiplication. Multiplication includes both multiplication by a number as well multiplication by the input. So when you multiply by the input, that's when the that's how you get, as a particular example of what we have seen in the past, a power function. So so an example of polynomials that are not on that list yet are the power functions that we have seen already. So it is when there's only multiplication by itself. So x to the third is x times x times x, and so on. As many repeated multiplication by the input. So these are power functions. We know pretty much everything there is to know about them. We have their graphs. We know the domains and everything. As always, remember odd are we know also a little bit about their symmetry. So cubical ones have remember the symmetry, the central symmetry, while the odd. So these are odd, and then even ones, they all look like this. The odd powers look like that. The all even powers look like this. Okay, and well, so that tells you right away things about the symmetry to begin with, as well as the second one has mirror symmetry about the y-axis, and it also tells you the range. So the range of the first one is everything, and the range of the second one is not. So these are two typical behaviors of polynomials, and these are to be kept in mind. So just about, except if you zoom out, that's still to be established. But if you zoom out on a polynomial, on the graph of a polynomial, you will see either one or the other picture. Okay, so the difficulty that we have to deal with is it is more than what if we zoom in. So that's a question that. Well, just as important, but if we zoom in, then there might be in the middle, the behavior might be like this. Okay, so it might be crossing the x-axis many times, and those are for us to find. Okay, so or like this. Okay, so there might be, and we call them x-intercepts, and so the x-intercept, finding them is a crucial ability that we need to develop. Okay, but so we have linear quadratic. We have all the linear right there listed. So m, as we vary m and b, we get a bunch of different linear polynomials. M varies the slope, b varies the y-intercept. Similarly, we have 3 parameters for the quadratic one. You vary a, b, and c, and that varies things as we already know what it does. C definitely varies how high it is located, and a, what does a vary about the polynomial, about the quadratic polynomial? If I change a, what's happening to the polynomial? Yes, and yes, but I would rather say it's vertically. It is more vertical, even though we know it is the same thing pretty much. But if you want to be careful, it is a vertical transformation, and don't forget the flip. So if a suddenly becomes negative, you have a flip. In fact, probably I could make a picture here. So a, say 1, then a is equal to 1/2, a is equal to 0, a is equal to -1/2, a is equal to -1. So suppose a runs through these values, and we start with some kind of a polynomial like this. Well, let's say a quadratic polynomial might look like this. Let me move it slightly off. Suppose this is my quadratic polynomial, ax squared plus bx plus c, and then I start varying a. Okay, then what's going to happen is there will be shrinking, vertical shrinking. So I move from a equal to 1, so a is a equal to 1, and then I move a to equal 1/2, which will make the whole thing sort of shrink vertically. So it will look like this. And as a is equal to 0, what's going to happen is it's going to turn into let me get rid of this, ax squared. Y is equal to ax squared. Okay, so the polynomial becomes flatter, and then it becomes what? A is equal to 0. It turns into into it is crushed into the x-axis, right? So move this around a little bit like this. So a is equal to 0. This extreme case, it becomes horizontal, and then as we progress to negative values of a, it becomes turned upside down, and then still flat, and then as we get to a equal to -1, we have finally the upside down version of our parabola, like this. Okay, so imagine this in a little clip. So start with a parabola, then parabola starts to get flatter and flatter and flatter, flattens out entirely, and then branches start to point down, and then turns into a parabola opening down. Okay. Okay. So now how do we study these polynomials in a way that we're going to study these polynomials in a way that is not similar to the quadratic and linear polynomials, because those are just too simple. We want to find whatever we can that would be applicable to all polynomials. Number one is to find the standard form. So what is the standard form? These two polynomials are written in the standard form. Okay, so this is standard form. Standard form as opposed to this one. This is non-standard, if you like, because of this kind of consecutive recursive computation that you carry out. The standard form, that algebraic form, that you look at it and you can tell things about the behavior of the function, just like with these polynomials. Like I said, we're looking at those two numbers for linear polynomials. We can tell just about everything there is to say about the polynomial. Same with the quadratic polynomials. Knowing a, b, and c will tell you roughly, at least roughly, what the graph looks like. So what about general polynomial? And this is what the standard form is. The standard form of a polynomial. So as you can see, we will follow, let me copy this, we will follow the idea of well, let me take the whole thing, of linear polynomials and arrange them in such a way that, copy, and paste. What the hell happened here? Oh. Okay. So what do they have in common? What do they have in common? Why, if you just arrange these terms in a well, you can see that can you tell me what these two representations have in common? So the linear and quadratic, what do they see that they have in common? Well, the v is just a name, so I wouldn't worry about that. That is certainly a similarity, but it is more of a coincidence because as we move on to cubic polynomials and higher, there will be so many letters that so many coefficients that we cannot use any particular letter anymore. So the similarity is look at axes. Look at axes. Axes in the terms. How many terms? Well, let's try to look for patterns. Two terms. 3 terms. Okay. So what kind of term? Term meaning this. How do you classify these terms? They are classified on the manner in which x appears. Okay, look at this. This one, no x. This one, x. This one, once again, no x. That's the similarity. Both of them have a term with no x, and both of them have a term with just one x. Okay, so that is the similarity. So those two terms in linear polynomial, they appear in almost exactly the same way, just under different names in the in the second line. Okay, it is what the difference is. This is the difference. The difference is x squared appears in this term, and that is the difference. So the other two terms are similar, and this term is dissimilar. Okay, so that's how we progress to more and more complex situations. So let me try to move in that direction. I will align them better, MB and MX. Okay, and here I have BX plus C, and here I have AX squared. Okay, you see the alignment now. The last kind of column aligned are constant terms. Every polynomial has one, even though it could be 0. Okay, the next one terms, so these are the constant terms. Constant meaning they don't depend on x. These terms are called linear terms. And naturally, this is called the quadratic term. Term. Okay, so you can guess what's going to happen in the next level. So linear, quadratic, now cubic. So what cubic polynomial look like? It will be x cubed. So say, I don't know, pick a different letter. So there will be a better match. Say ABC. How about D? Dx cubed plus ax squared plus bx plus c. In fact, how about I change the terms to create full illusion of similarity like this. Names don't matter anyway. So as you can see, that's we are seeing the how we introduce every time we progress down of this list. We add a new term of a power. Okay. So the constant terms on the right, then we have linear terms next to the left, and the quadratic terms and the cubic terms. And what the difference between quadratic and cubic? The presence of the cubic term. Then you go to fourth degree polynomial, then there will be yet one more term. So it's always possible that each of these terms might be 0, but we do require that the first term is not equal to 0, because that is the term that makes a difference. So the difference between linear and quadratic polynomial is the quadratic term, so we require for the quadratic polynomial to not to be equal to 0. Okay, otherwise you have bx plus c and you have a linear polynomial. Okay, so you don't want confusion. So and on. Okay, so that creates hopefully a pattern of polynomials that you see where it's going, so let's try to and that will be the standard form of a polynomial. Except what the difficulty arises is with how to use what notation to use for those coefficients, and they are the coefficients. So every time you have two coefficients, 1, 2, 3, 4 by the number of terms. So the number of terms is the number of coefficients. So you have 2 coefficients, 3, 4, and 5, and there will be on and on. And then cubic, we run out of words here also very quickly because there's a special word for every polynomial, and we want to have all the polynomials at once. So the way we describe it is nth degree polynomial. It will have n plus 1 coefficients. Okay, so to try to write it up, when you have n terms and n is unspecified, you want to have properly named terms. So let me not jump to nth degree right away. Let me do fourth degree first. So the one that follows the cubic one. So fourth degree. So it will be how many coefficients? 5 by the number of terms. Okay, so this is how we write it out with the coefficients. There's 5 coefficients, so they will name them A0, A1, A2, A3, A4. So it's a letter with a subscript. The point, once again, you don't want to use up all the alphabet to designate those letters. It's already cubic. It's already a little bit awkward. For fourth degree, it is even more awkward. So that's the choice that we make. We'll have coefficients, and we name them, like I said, in the proper order. And in the we just usually put an A, C. That doesn't matter what the letter is, but it's followed by a subscript indicating its location. Location goes from right to left. So here's what it looks like. A4 x4. Well, the wrong place. x4 A4 x4 plus A3 x3 x cubed, that is. A2 x squared. A3 A1 x. Why A1x? Because x is to the first degree here. So that's the match between the powers. And the last one is A0. Why is it called A0? Once again, you see a pattern of matching of powers and those subscripts. So A0 matches what? It's a 0. Okay, so what's the role of the 0 here?
It's not an x.
What?
It's not an x.
Right. So, but why 0? There is no x. Right. X 0 power of x is 1. So that's the logic. We don't have to put it in because we know that x to the 0th power is equal to 1. So we don't put it in, but the match, the pattern continues. So a match of the subscript in the power of x continues on from left to right all the way down to 0. So A0 is matched up with x to 0 power, which is 1. Okay. So that's the logic. Once again, we require A4 not to be equal to 0 to call this polynomial of degree 4. And so that's how we work it out. The nth degree polynomial, at least is a starting point. Let me write it once. We'll get back to it, but you can imagine that it starts with an xn, an minus 1, xn minus 1. So it's a little bit cumbersome, and then you have this dot thing, which is always confusing, but it is to indicate that we are continuing with the pattern. So the index of a goes down by 1, as well as the power of x goes down by 1, until you reach the point where we are in the place that we have been before. So this part is the same. As you can see, each polynomial includes a polynomial of lower degree in it. Okay. So as you can see, the fourth degree polynomials, if you remove the first term, which you cannot, but suppose you cover up the first term, then the rest of it is a cubic polynomial. If you take a cubic polynomial, cover up the first term, you're left with a quadratic polynomial. So that's the point of this kind of arrangement of terms like this. Okay, so every time you recognize the terms that you have seen before, and then you know that you're adding complexity by adding this extra power. So extra power term is added to the lower degree polynomial. That creates a polynomial of high degree. Okay, so this is what the nth degree polynomial looks like. Nth degree polynomial. Once again, we require an not equal to 0. And this is nth degree polynomial in its standard form. All of these are in the standard form. So what is the standard form? So it's made of, if you want to just look at the formula, it certainly is revealing, I think. But you can try to describe it in a manner that is also unambiguous, and that is so it's made of powers, right, up to n, made of powers, meaning x naught, x1, x2, xn, with coefficients, and then add it together. So that's what it looks like algebraically, even though you might not be necessarily computing in this fashion. And if you have a problem, sometimes polynomials appear, but they might not be in the standard form. So if you want to analyze it, you can right away see what it might take some work to put it in this form. Okay, so the two things, the very first and the very last coefficients, determine a lot about the behavior of the polynomial, and what is the meaning of A naught? Well, you know, so meaning of A naught? What's the meaning of A naught if it is a linear polynomial? Right, plus C, so what's the meaning of C? It is either shift, but it's simply the y-intercept, right? So that's what C is. But then you move to quadratic polynomial. What's the meaning of C? Quadratic polynomial, what's the meaning of C? Yes. Okay, what about cubic? What's the meaning of C? Y-intercept. They all y-intercepts, yes, because look at it. What's the meaning of the y-intercept? Meaning of the y-intercept is the value of which you get when you plug in 0 into the function. Okay, so if this is my function f of x, I plug in f of 0, every single term will disappear except for the last one. So the meaning is the y-intercept. Okay, it's not as easy with the first term, but it will determine the behavior of the function dramatically long term. Okay, so it's like short term is the very first, the A naught determines the y-intercept, so it's kind of important, but it is a behavior on a very small scale. Where is it gonna end up? A large scale is where the question is answered when you zoom in, such as those pictures on the right. Does it go to infinity, and which infinity? It will always go to infinity, but which infinity remains to be determined. So these are two different topics. One is about large-scale behavior, zooming out, and small-scale behavior. It is y-intercepts. We already have solved the problem, and then these are the x-intercepts. Over here, these are the x-intercepts. So that's a challenge. How to find x-intercepts, and the challenge is so much so that it is not cannot be easily solved, or sometimes cannot be solved at all. So the meaning of A naught is that it is the y-intercept. Okay. Okay, so we're not going to pursue this. We're going to pursue something slightly different, and that is once again what we know, a couple of things about linear quadratic polynomials, and we're going to use that information, those ideas in order to provide similar ones for general polynomials. Okay, so and that is factoring. Okay, so once again, if you take a linear polynomial, f of x is equal to mx plus b, the only way to factor is just, we're assuming that m is not equal to 0, so we can just factor m out, and have x plus b over m. It has been factored. Okay, so this is what we call typically a linear factor. Why is not, I did not take the original one, after all, the linear polynomial is a linear factor to begin with. This is more advantageous because we can look at it and we can tell right away the meaning of this. What's the meaning of b over m? It is, but it is something even more explicit. It is, in fact, the negative b over m is the x-intercept. Okay, so what is the meaning of x-intercept if not the, well, let me state this for the record. So given y equal f of x, a function, a value of x, say c, x naught, is, well, no, let's call it c, is called its x-intercept. We all know what it means. It's on the graph means that it crosses the x-axis, right? But what does it mean algebraically? So this is the c I'm talking about. The value of x, it's called its meaning the function's x-intercept. If what? What's the meaning of this point? It lies on the x-axis. What does that mean? That's right. So f of c is equal to 0. Okay, f of c is equal to 0 is what makes it y-intercept. As you can see, it is easily you can have many y-intercepts. So that's the challenge. And if you want to be connected to what we have talked about just recently is the x-intercepts, and we might need all of them, are the solutions of the equation f of x is equal to 0. So every function produces an equation. Solving that equation will give you all x-intercepts. As simple as that. So every function comes with that problem implicitly stated, and then whether or not we can solve it is a second question. So anyway, so for linear polynomials, the problem is automatically solved by means of it is solved the finding x-intercepts if you factor out m. You factor out m, and then for a linear polynomial, negative b over m is our x-intercept. Okay, so that's the advantage of factoring, not just finding those intercepts. It's the same function as it was before. It's just put in a different form. So remember, we just talked about the standard form, which is definitely not a factored form, right? So just look at it, how different it is. The elements are spread out. The elements are spread out with addition between them. Okay, so all of these. So what we're after is something entirely different, and that is a factored polynomial. Okay, so so linear polynomial is very easy to factor. Now let's try quadratic. It's not as easy. So f of x, once again, let me use the same notation. Well, here's the question. How do we factor a quadratic polynomial? How do we factor quadratic polynomials? Any recollections?
Grouping.
What?
Grouping.
Yeah. Well, you're thinking right. I maybe I didn't ask the right question. So I'm not even really asking about how. What does it mean to factor it? What it means to factor it? Let me write out what I mean here. This is what it means. This is what a factored form look like. So once again, this is the standard form. Decreasing powers from highest to lowest. And then the standard form is in the main operation, as you can see, addition. So all those powers are taken and then they're added together. Okay, here it is very different. So you have linear terms and they're multiplied together. They're very, very different forms. And they, as you can see, they serve very different purposes. So the standard form helps you to see, first of all, the x-intercept, y-intercept, the last element. It also shows you the so-called leading term. This is the leading term, which will tell you, remember, it tells you whether or not the polynomial opening up or down, whether it's slim or wide. But so these are the set of questions that the standard form tells you right away. But the factored form tells you what? It tells you, what does it tell you? If you already have the factored form, you're looking at it, what can you read off of it? What's the meaning of x1, x2? No, they are x-intercepts. These are the x-intercepts. Well, the definition right there, if I plug in f of x1, what do I get? I get a x1 minus x1, x minus x1 minus x2. So a times 0 times x1 minus x2, and it certainly is equal to 0. F of x2, once again, a x1, x2 minus x1, x2 minus x2. So also 0 in the same manner. The factoring is, and x-intercepts, they come hand in hand. So if it is factored, you can just look at the factored form and read the x-intercept from there, and vice versa. If you know I have two x-intercepts, you have found the factored form. Okay, so that is pretty much the approach that we take with polynomials, factoring polynomials. This is why we care to begin with, because we're looking for x-intercepts. The difference there will be many more factors. So cubic polynomial may have up to 3 factors. And so on. Nth degree polynomials will have up to n factors. Okay? So let me write it. So theorem, just for now, an nth degree polynomial has up to n linear factors. So f of x will look like this. I mean, ideally, it may have n, but it might have fewer. So that's the next topic to explore. So it might look like this: x minus x1, x minus xn. This is the largest possible factorization there, where there are exactly n factors. But in general, it's not the case. So it could be very important to remember. In addition to this, it's possible to have from 0 to n factors. Okay, so let's take a look at it. Is it really possible? And the answer is, well, it's not actually possible with the linear polynomials. We already did that. So mx plus b is always, this general linear polynomial can always be put in the form of mx plus b over m. And that, so it has been factored. So one factor. So it's always. That's the thing about linear polynomials. It's always has the one linear factor. What about quadratic? Ax squared plus bx plus c. Okay, so we know that x1 and x2, that's the factorization, is at the top. They are x-intercepts. So x1, x2, the x-intercepts, if any, they found from how? How do we find the x-intercepts of the quadratic polynomial? X-intercepts of a quadratic polynomial? No. I mean, you know the answer. You just it is probably the most basic thing about quadratic polynomials. Yes. Oh, well, yes. Sure. Yes. And then what do you do then? You set it y to 0 rather. No, x to 0. If you set x to 0, you'll get y-intercept. We're looking for x-intercept. So you set ax squared plus bx plus c equal to 0 and solve. And how do you solve it? How do you solve what? What? Right. Well, also known as the quadratic formula. I don't want to write it because we don't have this luxury when we do higher degree polynomials. So we just say that for quadratic polynomials there is a way to find the x-intercepts by using nothing but the quadratic formula. Okay? If that is the case, then there's a chance that we're going to end up with this. Okay? But that's one chance. So that's one possibility. What other possibilities do you know? Well, let me be specific. X squared minus 1, suppose this is our function. I'm factoring. It gives me x. How do we factor x squared minus 1? X plus 1, x minus 1, which gives me, by the way, once again, reading off what I'm looking at, is that these two are plus or minus 1. Okay, so these are the x-intercepts. And the factors are there. So 2 factors. How many factors can we have other than 2? We can have 1. Can you suggest an example?
If it's square.
If it's square, so say...
X minus 1 times x minus 1.
Right, yeah, so how about... So I put it first in the standard form, x squared plus 2x plus 1. Okay, so, and then you're supposed to recognize it as a full square. Okay, and so there is 1 factor. Technically, that's I want to be careful here for the future. It is 2 factors. 1 factor appearing twice. Okay, so even though it is 1, let me put it this way, 1 x-intercept, but 2 factors. So it is touching the x-axis. So there's only 1 x-intercept in contrast to the first one. It touches the x-axis, and there is exactly 1 x-intercept, but there are 2 factors, even though it's the same factor, but it appears twice. We call it multiplicity. So the multiplicity is 2. There is a third possibility. Yeah, well, let's speak of x-intercepts maybe. So 2 x-intercepts, 1 x-intercept, and 0, right. 0 x-intercepts. So f of x, as an example, what? A quadratic polynomial that does not cross the x-axis or touches it. Well, you take the parabola and just push it up. You take the parabola and push it up, so x squared plus 1, right? So so it will look like this. No x-intercepts. So I don't want to say that there are no factors, even though we are not factoring. For the near future, I'll put it as 2 factors, but they're complex, as in complex numbers. It's part of this course that we have to discuss complex numbers. So anticipating that, we're gonna gradually move in that direction. But you can see the pattern here, and that explains why we care about complex numbers to begin with. Is to have this pattern that I will still want to factorize that third polynomial, and it can be done if we are allowed to use complex numbers. Okay. So otherwise, this is how we're going to be doing the polynomials. So every polynomials will be factored into n or less factors. Okay. All right. So we'll resume tomorrow. We'll just prepare questions for Friday so we can have something to talk about. Okay.